Hello everybody, welcome back to Algebra 2 online. So the plan for today is to actually start talking about our next unit, which honestly builds so much off of our quadratics unit. Basically we're going to start looking at what we call polynomials of higher order, which quadratics are polynomials, linear functions are polynomials. Higher order just means higher exponents basically. So the biggest exponent will no longer be like 2, like with the quadratic. It's going to be things like 3, 4, 5, 6. You'll even see x to the 10th things and stuff like that too. And since we're going to be dealing a lot with exponents and things, it's a good time to make sure that we're really good with exponent properties. Like we're going to deal with a lot of large exponents, and you're going to need to know how to deal with them. So I just wanted to review. All these should be reviewed from Algebra 1, but it's just good to kind of run through them. So when we have a product of powers with the same base, this is the one where, this is really just x times x, that's x squared, and then times x times x times x, that's x cubed. And so you just literally have 5 of them. So you just say x to the 5th. But the shortcut in this case is add. You can just add the 3 and the 2 and get x to the 5th. In this case, if you have powers of products, right, this is literally just like xy times xy. And in that case, then you can use the commutativity of multiplication and move things around. And you get x squared and y squared. So it's kind of like distribution is sort of what I'm going to call that one there. Meaning you can sort of distribute the 2 to both of these. That's not really how distribution works, so that's why I put it in quotes, but that is sort of the idea there. If you have powers of powers, okay, so here we have x squared and all of that is cubed. Since we really just have x squared 3 times, right? And each of those you can just add up 2, 4, 6. You have 6 of these things. And if you think about what operation gets from 2 and 3 to 6, it's not too hard to see that this is the time where you want to multiply. So a lot of times students want to mix this first one and this third one. But you add when they're multiplied, and you multiply when you've got the powers of powers there. This one is honestly very similar to the first one. If we have something we have a quotient of different powers but with the same base, so something like this example, I'm going to expand this first. So we have 5 3s up top, and then we have 2 3s down the bottom. And so we could start reducing, and those go to 1s, right? And then this would be 3 to the 3rd power is what we have, right? Which is 27. But if you think about the powers here, we got a 5 and a 2 and getting us to 3. The only way that that's going to work is if you subtract, right? So similarly to the first one, when you multiply, you add, and when you divide, you subtract. So I want you to kind of see the pattern there. It's kind of like opposites, right? Multiply, add, divide, subtract. And this one too is good to do. It's honestly very much like the second one here. So whether they're honestly multiplied or divided inside, it still works the same. Like if you have AB, n times, you just are doing AB times AB, blah, 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 times AB, and all those, there's n of those things. And so if you go and you just multiply across on a fraction, you have a to the n over b to the n, right? So this one is still just kind of like distribution. But again, I'm going to put it in quotes because it's not really distribution. But the idea is you're putting the n sort of on both these, just like you put the n on both these here. Okay? And those are kind of like the biggies. There's some special cases, and I'm actually going to show you those on the next slide here. So just to kind of be clear too about where we're going with all this. So So the name of the next unit is polynomials and polynomial operations. And basically we're going to solve things that are like x cubes, x to the fourth, x to the fifth. I even have some planned that are like x to the 10th. And this is kind of examples of what they look like. We're going to graph them. You're going to see patterns with the graph and similarities between quadratics in these guys, also linear functions in these guys. You're going to learn how to find all the roots of these and all sorts of stuff. There's a lot of really important things here. And the first thing, just to kind of get into this, is how we deal with some kind of really important basic polynomial like operations. And so that's really what today is about. We're not going to get into like the meat of solving anything like this yet or graphing anything like this yet. So really today, just how to work with big exponents, basically. And these two are special cases kind of related to what we were talking about on the last slide. And they're really the same things. All the properties on the last slide still apply, but they are special enough that I want to give them their own slide sort of here. So negative exponents. So if we have this case, right, this is just like the little example right here. And the property was that you could subtract the exponents, right? And you would get 2 to the 2 minus 6 is negative 4, right? But the students always ask me, like, what does negative exponents mean? It does not mean you're making anything negative. Let me just start out with that. Students always want it to think, like, something's going to be negative here. There's nothing negative. There's nothing negative in this thing at all. We're not going to all of a sudden have a negative number here, right? Really what the negative does is just tells you the side of the fraction it's in a sense. So if we go and expand things here, right, we have 2 over 2, or 2 times 2, and then we have 6 2's on the bottom. I think that's 6 2's, yeah. And then you can go and cancel some of those. And then if you look at what you got, you have 4 2's left over here and a 1 up here. So when we see a negative exponent, it just means flip like the side of the fraction where the thing is, right? So honestly, if there's a negative down here, it means it actually lives on the top. If there's a negative up here, right, because this is like over 1, then it's just saying that it lives on the bottom of a fraction, really. It's honestly just a lazy math tool to say this thing is on the bottom of a fraction. These two things are the same. So the 4 is still the same old 4. The negative just does a different thing. The negative acts as like a flipping mechanism between the side of the fraction it's on. So 0 exponents, very similar also. Still use the same property. 3 minus 3 is 0. So this is why we've got a 0 exponent popping up here. And we also know that, 2 cubed, it's 8, over 2 cubed, which is 8. 8 divided by 8 is 1, right? And so we can see that if we do 2 to the 0, we're getting 1. And this is actually kind of a weird thing if you haven't thought about it. A lot of times students want to be like 2 to the 0 equals 0. And that's like reasonable to think about. We could get into it kind of a bunch more too. One really quick thing that I'll just sort of say. If we have like 2 to the 0 times 2, say cubed or something, we talked about how we add exponents, right? So this would be the same as 2 to the 0 plus 3, which is 2 to the cubed, right? And if you think about it, we're multiplying something by 2 cubed, and we're getting 2 cubed. And the only thing in the world that makes sense for that would be the number 1, right? The number 1 times 2 cubed equals 2 cubed. Equals 2 cubed. So it's just kind of another way to think about why this thing really should be 1. It's not 0, it is 1, okay? And like you can see it kind of this way, or you can see it this way, I guess. Yeah, so anything that's 0 power at all, not just 2 also. There was nothing special about 2 in this problem. I could have done 3 here or 4 here or 5 here or whatever. As long as whatever you put here, raise it to the 0 power, you get 1. There is one thing, I guess I will say. 0 to the 0 power is a bit confusing. This one you can argue about. It's a very interesting problem to kind of read about. 0 to the 0, it's a solid argument to say it's 0, but it's also fair to say it's 1. This is actually something in math we call an indeterminate form. And indeterminate forms show up actually in, you'll sort of see them in calculus or pre-calc a little more often, but there's some other ones in math that are literally, like, what this means is we don't really know. It's an area where the system of math we have built up kind of is broken, is the idea. So I'm not going to say too much about that. You can read about indeterminate forms on your own if you want. I'm happy to talk about them sometime, just not in this video. All right, boring definitions. This right here is like a general polynomial. It's actually what we call a polynomial of nth degree. But a polynomial is an expression consisting of variables and coefficients that involve only the operations of addition, subtraction, multiplication, and non-negative integer exponents. So if you have negative integer exponents up here, right? Like if we have x to the negative 2 or something, we just talked about that. That would be 1 over x squared, okay? And, we have like a function y equals x to the negative 2, or 1 over x squared. This thing is something we call a rational function. And we will study those, and we will see those. But they are not polynomials. Polynomials have to be non-negative exponents up here. So basically, all of these are examples of polynomials. And some of these are special enough that we have some other names here for them. So I wanted to kind of run through these. There's sort of 3 terms that we use that are special for the number of terms. If we have more than 3 terms, then we'll just start to say polynomial. And the polynomial, poly means like many. That's what that prefix means. So it's really just like, nomial is like terms. So this is really saying like many terms is what this is saying. But if you only have 1 term, mono means 1, we could actually call that a monomial, right? If you have 2 terms, then bi means 2, so it's binomial. 3 terms, tri means 3, trinomial. And then anything after that, we'd usually just say polynomial. But technically, all of these are also polynomials. It's just that these have like more special names to be like even more informative as to the amount of terms in the expression. Degree is about the exponents. So for constant functions, they are polynomials. It's just like you have x to the 0, right? Because x to the 0 is a 1. So if you do something like, if I'll do this over here. So if I have a function y equals 12, x to the 0, that like is a polynomial, has x's, and, it fits this definition. But then the x to the 0 is 1, and so we get y equals just 12. That is constant degree. That means degree 0. Constant, right, just because it's always the value of 12. It's never changing. It's constantly that thing. Linear things, not much I want to say about this because, honestly, even both of these, this is this is basically what you do in Algebra 1. Linear functions really well. It's degree 1. It's just x to the first. We just talked a lot about these ones, so I don't really want to say much about these also. This was, unit 4, and we just got done talking about tons of that stuff. But quadratic is the term, right, for degree 2. Cubic is a word I will definitely throw around a lot. It's just when the biggest exponent is 3. This thing is a quadratic, right? And it's trinomial, 3 terms. This one I will probably say pretty often still, but not as often. I might just say 4th degree, but you should know the term still. But quadratic is the fancy word for when your biggest exponent is a 4. Okay, and they actually do keep going. There's something called a quintic, which is like a 5th degree. And there's even more, but I thought 4 was kind of enough. And probably if there's any other ones that I just say or show up in a problem, I'll just take time to define it really quick. But I do plan on using these terms and these terms, so you should be familiar with them basically. And just to kind of help with that, I wanted to just do a quick example here where we write down examples of these 4 things. So there's lots of options for all of these problems, but I'm just going to write down one for each. So cubic trinomial means that you need 3 terms and the biggest exponent needs to be 3 because it's cubic. So the cubic part means there's like an x cubed. And then the trinomial just means that there's 3 terms. So something like plus, 2x plus 1. So there's 1, 2, 3 terms, trinomial, and the biggest exponent is x cubed. That is a cubic trinomial. Quadratic binomial, also tons of these things. You could do something like x squared minus 4. It's actually a difference of perfect squares. But it is quadratic because of the 2 and binomial because there's 2 terms. Constant monomial means that it's just a 1-term constant. An example of that is like y equals pi. That is constantly the value of pi. It's just 1 term. X to the 0 is really inherently there, and that's the part that's giving you the constant piece. But we don't really write it. We usually just write pi there. But that is an example of a constant binomial. It's something that's always the same value. And then we got a 4th degree or quadratic polynomial. So polynomial just means really 1 or more terms. So it doesn't need to be a specific number here. It could be honestly 1, 2, or 3. And maybe let's just do one of each. You could have negative x to the 4th. That's a 4th degree polynomial. You could have negative 7 13ths x to the 4th plus pi raised to the 3/2 power. That is a quadratic binomial. And then you could have like 7/15ths, all of that raised to the pi power times x to the 4th plus x cubed over 2 plus pi. And that would be a quadratic trinomial. But it is also a polynomial, because poly just means 1 or more. Really poly means many, but all of these are counted as polynomials. So the first kind of thing that your first assignment is going to revolve around just simplifying polynomial expressions. And these are ones that I don't really want to spend too long on because I think they're kind of straightforward. If I give you something like this or this, here you literally just combine like terms. I mean, this one literally, you have like terms right there, and you would get then 5m to the 4th. Then you have m squared, negative m squared and plus 5m squared. So then you would have plus 4m squared. I mean, that one's like really quick. This kind of stuff, right? You could like distribute and then do the same thing, combine like terms. This one here, just messier. You could go ahead and, just combine like terms. You just need to make sure that like, for example, this and this are not like terms because you don't have the same amount of m's and n's. So you have to be careful with like the exponents, right? And then this one, I also think you'd be fine with. This is actually something where you'd have to triple distribute. Actually, I'm going to do a different color here. So you'd have to distribute the x squared, and then you would have to distribute that second term, and then you'd have to distribute the -8. This one is what we call basically triple distribution. And it's actually why I don't like the term foiling for double distribution, meaning like when you have stuff like this, I don't like to say foil, and I hope you don't really know what foil even is. Foil is short for first, nope, I just messed it up. I don't even use it. First, outside, inside, last is what foil stands for. But really, you should just teach double distribution. So distribute once, distribute twice. And that would give you the simplification of that, this quadratic here. But that extends really nicely to higher order things because here we could just call this triple distribution. That's really what it is. So those are the ones that you should feel good doing them. And if there's any parts of these that you don't feel good about, you should ask. But the harder ones that we're going to kind of work on in the first part of this unit are the division. So there's technically two cases here. There's what I like to call the easy case and the hard case. And the easy case is what you're going to have some homework on first. So you could have something like this. And this is not bad because you only have one term on the bottom. When there's two terms on the bottom, you're going to need to do what I'm going to talk about down here. So for the easier case, it's honestly just like you've done it honestly before. Like if you have 2x plus 4 and you divide by 2, right? We know we divide 2 into both of those things and we would get x plus 2, right? We divide 2 in here and here and we get x plus 2. And it's no different with variables on top and bottom. So we would just divide 2x in there, and there. And what we would get in this is we also do the number as well, right? So we get 6x squared plus 8x minus 4. And then the x's in that last one go away. That one is nice because you can just go ahead and like divide this term into everything, and then you have a simple expression from that. If you don't have one term down here, so you have two terms or more, then you have to do this, and this is long division, right? And I'm going to have a whole nother video where I talk about how to do polynomial long division, and then eventually I'm going to even have another video where I show you some like shortcuts. There's something called synthetic division, and you're going to see basically a shortcut on how to do polynomial division even easier than this. But technically, there's really no other way to do it besides the long division. Even the shortcut is really doing long division. It's just doing it in a quick kind of way. But one thing I don't actually like about what I just had here is I want to show this part too. So when we do long division, right, we do this thing where we put something up here, we multiply, put it down here, and then we subtract. And that's what's going on in this this image right here. So we're subtracting these things, right? This is going away, and then you're doing 9 minus -18, and you get 27. And you're bringing that down, right? That's how like long division works. You bring that down, and then you bring this one down. So a whole other video coming up with that later. Don't need to worry about it right now. Just know that if there's more than one term, sorry, you're going to have to do this, okay? If there's one term, you can just go ahead and do this. So just the last little quick example here. Just want to kind of make sure that we're good with simplifying weird exponent kind of expressions. So let's just get into it. So probably lots of different ways to do these. One of the things that I'm just going to do first, the negatives, right, mean that it has nothing to do with negating the number. It just means it's on the opposite side of the fraction. So I'm going to write this thing as 2 times any of the negatives, basically. I'm just putting on the bottom is what I'm doing. So we have a squared down here and c squared down there, right? So that's just dealing with the negative exponents right there. Then we can go ahead and use like the subtraction kind of tricks. So, well, not here because those are different letters, but we can use it here. So we can cancel a squared with 2 of these. We'll have 1 of those left, right? And then I'm going to also multiply these. That's not too hard to do, right? So I was just waiting on that, but I'm going to just do it at the same step. So 2 times 3 is 6. And then we have 1a. We did nothing with the b's. And we have a c squared on the bottom. So maybe it doesn't look that simple, but it does look simpler than that, I would say. So those really mean the exact same thing in math. So this one, we've got, I'm going to deal with the 0 exponent and the negative exponent in the first step. So we've got anything to the 0 power, right, is 1. So we can do negative 2a to the 4th. And then we also have this a to the 4th here with a negative on the bottom means that's going to flip to the top. So we're going to have that. And then we still got b squared. We didn't do anything of that. And we got a cube. So all I did there was I dealt with the 0 exponent, which is 1, just disappears from the problem. And then this pops up to the top because it's a negative on the bottom. And then we can go ahead and when we multiply with the same base, we add exponents. So that could simplify to a to the 8th. All that's over b squared, and then all this is cubed still. Then we can go ahead and, this is the part that I'm kind of nervous using this word, but we kind of distribute that exponent right there. And we also we need to distribute it here too, right? That's definitely in there. So negative 2 cubed is negative 8. And then a to the 8th cubed. So I'm going to just write it like that for a second. And then b squared cubed. Everything just got the cube, basically. And then last but not least, when we have powers of powers, we multiply, right? So this would become a to the 24th, and then b to the 6th. And that is the exact same thing as this.